Hello, welcome back. Let's go a little bit deeper into nonlinearities. In the last video, we talked about dry friction and we introduced a model that can handle dry friction. In this video, we want to talk about something different. So, some of the nonlinear functions are the functions that are somehow sometimes present and sometimes they disappear. Okay, so they have a switching behavior: present, absent, on, off. Okay, 0, 1. And we want to model such a nonlinearity. Okay, so let's get into it. Let's go back to the solenoid valve. Okay, our underlying assumption when we wanted to model the solenoid valve was that the return spring is undeflected when the plunger is at the seated position. So somehow, miraculously, the gap here was the same length of the free length of the spring. At this point, let's assume that this gap is not the same length as the free length of the spring. Basically, the free length of the spring is bigger than this gap. So we first squeeze the spring and then put it in the gap. So there would be always a preload force that is always pushing the plunger and the spring, the plunger and the push rod and the spool to the left. We show the effect of that preload force as a constant force, okay, that is somehow a source, an external source. We model it that way. On top of this, you see that because we have the preload, when the plunger is at the seated position, there would be somehow a contact force that is applied from the wall to the plunger. Of course, the minute that the plunger starts to move to the right, you lose contact here, and this contact force will disappear. You see that? You have a present-absent behavior. You have an existing, non-existing behavior. And you want to model this behavior in this problem. Okay? So, in this problem, we also assume that we have a dry friction between the spool and the wall as well. Okay? So, let's get into it. I'm first going to list the elements in the system. Okay? If you look at the elements, you have inertia, stiffness, friction, also my sources, and the number of ODs. Okay? So, what is my inertia element? The same as before. It's going to be the mass. I have only one mass. My stiffness element is the return spring. I have two friction elements, the viscose damper and also the dry friction. My sources in this problem are basically FEM and F preload. Yes? And the number of ODs is still 1, okay? Because naively speaking, I have only one inertia element or one mass. Okay. Now, let's go to the 4-step approach. Step 1, I'm going to select a coordinate system. Okay. For the coordinate system, again, I'm going to pick X, started from the seated position, and pointing to the right. Okay. Note that at this point, seated position is not representation of the free length of the spring. Yes? So I'm going to have X, okay? And I'm going to work with this X. Step 2, I'm going to isolate my inertia element. Okay? So what do I mean? Grab that inertia element, disconnect it from the system, and throw it on a piece of paper. Yes? Okay. Step 3, it's going to be my free body diagram. So step 3 would be my free body diagram. Yes? For the free body diagram, I would look at view, CSR. Again, friction, external weight, contact, spring, rope. Okay, let's start with the friction. We have done this twice already. Okay, so I have a viscose damper, I have a dry friction. The magnitude of the viscose damper friction would be Bx dot. The magnitude of the F dry is a constant. However, in order to incorporate the direction, I'm going to multiply this by the sine function x dot. Yes? Okay. Now let's figure out the direction. If you assume that the box is going to the right, the direction of both of these guys are going to be opposite direction of the velocity, which is going to the left. This is done. Externals. I have F electromagnetic. And also, I have preload force, which you note that these guys are given to me. And F preload is always pushing to the left, and F electromagnetic is basically pushing to the right. The next one is the weight. Weight is applied at the vertical direction. I do not have a motion on the vertical direction. I'm going to neglect the weight. When it comes to contacts, I have two contact forces here in this problem. One of them is the normal reaction from the surface that's pointing upward. This one is useless in this problem. Why? Because I do not have any motion on the vertical direction. However, there would be a contact force that is, we show it with FC, that is sometimes present and sometimes absent. When the plunger is at the seated position and there is no motion, we have FC. The minute that the plunger starts to move to the right, FC will disappear. Okay, so and this is actually another source of nonlinearity for us that we need to model. The next one is the spring. And we've done this one before. Since only one end of this spring moves and the other one is clamped to the wall, the magnitude of this spring force is Kx. The direction, you figure out first whether the spring is in tension or in compression. Then from that point, you figure out the direction of that guy. So if the box goes to the right, you see that the spring is going to be squeezed, it's going to be compressed, and it's going to push against the direction of the motion. Okay, now looking at this problem, we think that we are actually done with the free body diagram because there is no rope in this problem. Okay, and we can go to the next step, which is the equation of motion. Yes, so for the equations of motion, we have summation of the forces along x equals to mx double dot. Yes, so let's look at this. I have a lot of forces here. Actually, I have 6 forces. These two are pointing to the right, which is the positive x direction. These 4 are pointing to the left, which is the negative x direction. Okay, so it's going to be positive FEM, positive FC, negative KX, negative BX dot, negative FPL, and negative F dry SGN X dot equals to MX double dot. Okay, now let's keep the inputs and FC also on one side, okay, and bring everything else to the other side. Let's see what we have. Yes, so it's going to be FEM plus FC equals to MX double dot plus BX dot plus KX plus, I forgot to put FPL as well here. Okay, so let me just push these ones a little bit to the right. Okay, so I'm just gonna push these guys a little bit to the right. Okay, and add FPL there. Okay, so with the sign FPL negative. Yes, MX double dot plus BX dot plus KX plus F dry SGN X dot. Okay, and basically what I did was I just bring all the dynamic terms to the other side and flip their signs. Okay. However, guys, we still need to take care of FC. We have not taken care of this yet. Okay. Now, you notice that when the plunger is at the seated position, okay, and your X dot is 0, your X is 0, your X double dot is 0, okay, then you have basically FEM plus FC minus FPL equal to 0. Yes. So in a way, when you do not have motion, your FC is in fact equal to the difference between FPL and FEM. Yes, the difference between FPL and FEM. Whenever you don't have a motion, okay, the minute that you have a motion, then your FC would be disappearing. Where do you have a motion? Okay, so this is the time that basically your FEM is less than FPL, which means that your F electromagnetic is smaller than the preload. It's not as strong to overcome the preload and basically move the plunger to the right. However, anytime your FEM is greater than or equal to FPL, okay, then you'll see that you overcome the preload, you're gonna start the motion, okay, and the FC would disappear. Okay, and this is the behavior that we have for FC. Okay, and you see that FC happens to be present, okay, which is going to be, when it is present, it's going to be the difference between FPL and FEM. And sometimes it's going to be absent, it's going to be 0. When you start the motion, or better wording, when your FEM is at least equal to the preload. Okay, that's it. So if you find this video helpful, please don't forget to subscribe to the channel and follow the full list for future videos. Thank you.